We shall be looking at IEEE addition now, how we can add two numbers or two decimal numbers after representing them in IEEE 754 floating point representation. So for example, let's assume that the first number x is 5.873. So x is 5.873, and we have another number which is y, and let's assume y equal to 3.573. 3.5, sorry, let me erase this one. uh, 3.573. We know how the straightforward addition would look like, or how can we do the straightforward addition, but how we can perform the addition using IEEE 754 floating point notation. To do that, the first thing that we need to do is we need to convert x and y into normalized form, or represent x and y into normalized form. So what would be the binary equivalent of x? So the binary equivalent of x would be 5 is 101 point this 873. If you do the binary representation, or if you keep on multiplying this 0.872 by with 2, then you can get the binary equivalent of 8.873. This value would be 110 then you will have 5 ones, 5 ones and 0. This is the binary equivalent of 5.873. Now our next part would be to represent it into normalized form, which is 1.01 and then 110 1 2 3 4 5 0 into 2 to the power 2. So this is the normalized representation of x. What about y? So for y, we know 3 is 1 1, and now 5 7 3 is 1 double 0 1 double 0 1 double 0 1 double 0, and then 1 0 1 0 1 1 0 1 0 1. Again, what would be the normalized representation of this one? This is 1.1 100 100 1010 and 1 into 2 to the power 1. Now the rule of addition, when we are performing addition of two numbers, the rule of IEEE 754 floating point addition is that we need to make sure that the exponent, both the exponent are equal. So we need to make these two exponents equal, and the algorithm that is used for performing IEEE floating point addition says that makes the lower exponent equal to the higher exponent. So in this case, we can see that in y we have exponent 2 to the power 1, and in x we have exponent 2 to the power 2. So what can we do? We can make exponent of y to go to 2. So we can write it like this: 0.1110001001 into 2 to the power 2. Now we can see that both the exponents are equal, so we can perform the addition then. So we can perform the addition x plus y, which is 1.0111012345 plus 0 0.111001010101 into 2 to the power 2. So if we perform the addition here, then what we'll get, once we perform the addition, then we'll get 10.1010 and then triple one triple zero triple one triple zero and then 1 1, then 1 1 into 2 to the power 2. So what we can do here, we can make it 0 just by doing this 1 and shifting the decimal point the right, and then mm, 0 1 2 3 0 0 0 1 1, and you can write something like this. Now when we perform the uh, we need to come up with the decimal equivalent. We know this part is 9. This part is 9 plus we need to write this is minus 2. This one is minus 2. So we all know this one is minus 2. Sorry, having some trouble with this one is minus 2, and then the next one is minus 3 and then minus 4 and so on. So if we write it like this, 2 to the power minus 2 plus 2 to the power minus 3, 2 to the power minus 4, and for this 2 we'll have 2 to the power minus 8 and 2 to the power 2 to the power minus 8 plus 2 to the power minus 9. So if we uh, generate the decimal equivalent of this value, this is 9.4433. So this is our decimal equivalent of the addition, if of the addition of x and y. Now if you perform the actual, or if you try to come up with the actual addition, then you can use your basic arithmetic, and you can come up with the addition, actual addition of x plus y, which will be 4.996, sorry, 9.446, sorry, it's 9.446. So this is our actual value, and this is the one that we get after performing the addition using IEEE 754 floating point notation. As you can see, the addition, the floating point addition performed using the IEEE 754 method gives you a little less than the actual value. This is because we did not consider all the binary values that could be possible for the fractional part. For these two fractional part, we did not consider all the possible binary combinations. We restricted ourselves at certain point. If we consider all the binary points, then we would get close to the additional value, or close to the actual value, or uh, exactly uh, actual value. Let's discuss another example where we have x equal to 0.321, 0.321, and y is equal to 0.0123, 0.0123. As always, we need to convert x and y into binary equivalent. So the binary value or binary equivalent of x would be 0.0.010, then 1001, 1001, and y would be 0.60, 0.60, 1, 2, 3, 4, 5, 6, and then 1, 1. To make x normalize, that would be 1.01001, 1.01001 into 2 to the power minus 2, and the normalized form of y would be 1.1 into 2 to the power minus 7, as you all know. So performing, by the way, we are performing x plus y. I forgot to tell that we are performing x plus y. So to perform x plus y or x minus y, we need to make these two exponent equal. To make these two equal, we need to make minus 7 go to minus 2. So which would be this 1, 2, 3, 4, and 1, 1 into 2 to the power, and to make minus 7 to minus 2. So this is minus 2. So now x and y, they both have the same exponent. So so now we can perform x plus y, which is 1.01001 plus 0.00011, and the exponent is 2 to the power minus 2. So if we just let me erase this one and then write it. So this is all 0. So the final addition would be 1.010 1.0100101 into 2 to the power minus 2. Then you can so this would be 0, 0, 1, 0, 1, 0, 1. So this is minus 2, minus 3, and this minus 4, minus 6, and minus 8. So we can write 2 to the power minus 2 plus 2 to the power minus 4 plus 2 to the power minus 6 plus 2 to the power minus 8, which would give us 0.332. This is the value IEEE. When we apply IEEE 754 floating point addition rule, and the exact value x plus y exact would be 0.333. As you can see, both of these values are very close, so we can say that the result that we got using IEEE 754 floating point representation is correct one. Next, we will see how we can perform the multiplication. To do that, let's assume two values x equal to 3.751, 3.751, and y equal to 4.371, 4.371. So how can we perform the multiplication? The first thing is we need to convert both the values into binary equivalent values. So 3 is 11.11, okay, into 2 to the power 0. This is the binary equivalent of x. Now to perform the normalized form or generate the normalized form, we'll write into 2 to the power, sorry, 2 to the power 1, okay. And for y This is 101.010 and then 4 ones. 010, then 4 ones. 1, 2, 3, 4 into 2 to the power 0. So 1.0100 into 4 ones into 2 to the power 2. Now we can see that x has exponent which is 1 and y has exponent which is 2. In case of addition, what we did, we made both these exponents equal to perform the addition operation. But when we are performing the multiplication operation, we do not have to worry about that. Once we are done with the multiplication, we can just add this exponent. So now our purpose is to perform the multiplication, which is x multiplied by y, and this is 1.111 into 1.010101234, and what did we say? We are going to add the exponent, so this will be 3. Now if you do regular binary multiplication, the final result that you are going to get is 10.4040 and then 101 101 and then again 40 and then 1 into 2 to the power 3. So this will be 10 and then 1 2 3.010100001, and we can write 2 to the power, sorry, 2 to the power, this will be 2 to the power 0, so we can write 2 to the power 0. Now the binary decimal value that will get if we do the if we take the positional 1 and do the addition, the decimal value that we would get would be 16.314. This is the equivalent value, and the actual value that we get after the multiplication with regular multiplication would be x y would be 16.396. 16.396. So we can see that both the results are almost similar. Let's do another multiplication. X equal to 5372, 5.372, 372, and y is 3.537. 3.537. Before we perform the multiplication, let's see what would be the actual exact result. X multiplied by y would give us 19.0007. So this is the actual result that you could get if you enter these two values in the calculator. Now let's convert x into binary form. So this would be 5 is 0101.372 would give us 010 and then 4 ones, 1 2 3 4. Let's write 2 to the power 0 with this one. So the normalized form would be 1.010101234 into 2 to the power 2. For y, this is going to be 11 point for 5537 would get 1 1 and then three zeros and then 100 100 into 2 to the power 0. So the normalized form would be 11000100 into 2 to the power 1. Okay, so the multiplication would be, let's erase this one. So the multiplication of x multiplied by y would be 1.01010123 multiplied by 1.11000100 into 2 to the power 3. So if you perform the regular multiplication, then what you would get something like this: 10.01010, then 4 ones, 1 2 3 4, and then 0000, and then you would get 6 ones, 1 2 3 4 5 6 into 2 to the power 3. So 10010 into 4 ones, 1 2 3 4 00 1 2 3 4 5 6. So the equivalent decimal value that we can get from this binary representation would be 18.96. Now if you compare this value with the value that we could get using calculator, you'd see that they are almost similar. If we take more values, more binary values after the fractional part, then we would get 19.0007 or almost that. Even though the value that we get now 18.96 is, if we again this is like 19.0. Okay, so these two values are the exact value, and the value that we get after the IEEE 75 for floating point representation or multiplication is same. Let's add two binary values. They are represented in hex. So let's, the first value is a. Let me erase this one. So the first value is a, which is 7acb, 7acb, and the rest of the four hex digits are 0. And b is 32ab, 32ab, rest of the hex digits are 0. So the first thing that we need to do, we need to convert this hex digits into binary. So 7 is 0 1 1 1, a is 12, so sorry 10, 1 0, c is 12, so 1 1 0 0, b is 11 1 0 1 1, and the rest of the digits are going to be 0. So we can see that the MSB bit is 0, so the value is positive. So what is the biased exponent that we have here? 4 ones, 1 2 3 4, 0 1 0 1, 0 1 0 1, which is 245 in decimal. We all know that inside this 245 we have 127 as the biased value. So we need to take it out to get the actual exponent, which is 245 minus 127, which would give us 118. So the normalized representation of A would be 1.1001000 1 1 0 1 1 1 1 into 2 to the power 118. And for B this 3, so 0 0 1 1 0 0 1 0, and A is 10, so 1 0 1 0, B is 11 1 0 1 1, and the rest is 0. So similarly, the MSB bit is 0, so B is going to be a positive value, and then the exponent Q is 0 1 1 0 1 1, and then 0 0 0 0, and then 1 0 1 1 0 1, which would give us 101. So our actual exponent E would be 101 minus 127, which is minus 26. So the normalized value of B would be 1.0101, 1.0101, 011 into 2 to the power minus 26. Now for the condition of addition is that we need to have both the exponent equal, but for A the exponent is 118, and for B the exponent is minus 26. So we need to make minus 26 uh, equal to 118. That means we need to change the exponent of B equal to 118. How can we do that? We can do it like this: 0 and 0, then there will be few zeros, and then 1 0 1 0 1 0 1 1 into 2 to the power 118. Now to go from here to here, how many ones do we have here? How many zeros do we have here? We have in total 143 zeros in this part. Okay. Now, if we perform the addition, then what we'll get A plus B is this 1.1001011, and then lots of zeros. Then we'll have lots of zeros, and then we'll have 1 0 1 0 1 1 0 1 1 into 2 to the power 118. Now if we perform the simplification, and then we take that means we take the decimal point in the equivalent to the right for adjusting this exponent, what we'll get something like this: 1 1 0 0 1 0 1 1 0, and then lots of zeros, point. So we'll have a point here, and then again few zeros, and then we have 1 0 1 0 1 0 1 1. This is what we are going to have. So how many zeros we are going to have here in this part? In this part we are going to have 101 11 zeros, and in this part we are going to have 18 zeros. We are going to have 18 zeros. Now if we convert this into equivalent decimal values, then what we'll get 5.2727 into 10 to the power 30, 10 to the power 35. So this is the equivalent decimal value that we'll get once we perform the addition of these two hex values, which is actually binary values. So that means when you perform the addition of a binary value A and binary value B, we'll get this decimal value.